hello, nice to meet you. It like goes up the sleeve. If it's like somebody he knows, he'll like go all the way up your sleeve. I hate it.
Your partner's uncomfortable.
He does it on purpose to fuck with people. It's not like he just does that.
Nice to meet you.
What brother?
Can I ask you a question?
The devil is like at the end there.
He's the youngest?
He's the middle one.
I'm gonna get this down.
He's the skinny, irritating one.
Okay.
Is that the one you're
They're all
on the fight?
irritating.
Is that the one you have to fight?
No, Sal. Hi, John. How's it going? Will you do my homework for me?
What's up?
Told you, I'm like
Impervious.
to tickles. I am trying that body reaction down.
What do you mean? Like mentally, do you feel it? You just ignore it? Is that
Yeah,
what you mean?
years of practice, no reaction.
Wow.
Years of practice, no reaction.
I'm gonna have to wait for the
She's so
I feel like I won't.
I feel like I know. No, actually, because you lose. I lose feeling.
Yeah. Yeah.
I was gonna make a joke, but then it was a really bad joke. I'm like, it would have been super bad.
Okay. I don't know, I think it's like, the only places I'm like really ticklish would be places that like.
15 minutes and.
No, not even my feet, because like my brother used to try to tickle my feet, so like that, I shut that off now.
I hate it.
Like, you know when people do that? And like, if somebody like grabs me stuff like side does that, I don't react.
Yeah, yours is gonna go fast.
Cheers for
I haven't
that.
had a whole day.
I've shut that shit down.
I just feel very proud in all of this. Like everything is like
Place yourself here, alright?
right there.
Give me a whole
No,
thing.
I was gonna say, this is big.
How did it go?
Well, I really don't have any.
Wait, stop. Yeah. And there was like a little ham. So square.
Yeah,
Which setting is the dryer over?
15 minutes, no.
5. Show the
Right.
torches.
What?
Which setting does the dryer work?
Only on the high heat setting. The high heat setting. Only I put some in last night on the regular setting.
Stick your butt.
yeah, my butt.
I don't.
It's like the pop top.
I would be uncomfortable. I would be uncomfortable. Like,
Yeah, we call ourselves for.
Yeah, well, one side, if like high heat low heat.
This hadn't happened to me.
we're pretty sure, right? Because the dog Jeff, he's a huge Alaskan Malamute. He's 20 pounds. He weighs 20 pounds more than me, right? He's a dog. And he like has this thing where he like throws out and like shoves his head.
Like a million
across
years
it.
ago.
And it's like the worst. They're so weird.
I was so mad at trying to working out of this last night.
I was super irritated. I was just like, so bad. I was trying to like get her to put the food up and she was just like, who are you?
But like, it would have happened if I walked in there.
Yeah, but then like you came in and she got scared, just did a roll over, like, no, please, I surrender.
Yeah, I was just like, go back to bed. And she was just like on the floor.
Like, she didn't even go back to the book.
I was just like,
I'm not sure. I won't be here.
What?
okay, I'll do it this time.
Look at you, Michaela, taking over.
I know, well, I haven't done this in a while.
You don't win. You don't win at anything. Just dusted a million Pop-Tart crumbs off of your seat. Just like, while you were going
Yeah.
Okay, I don't get it. Maybe if I like got that chair.
Alright, so on Monday, where we left off, right, we said, let's envision that when we're dealing with a special case of irrotational flow, that is flow for which the curl of the velocity field is equal to 0. Right, we can define some special function which we called the velocity potential, phi, such that u was equal to d phi dx, and v was equal to d phi dy. And if we define the velocity field this way, then for any choice of phi that we could come up with, this was satisfied intrinsically. So this is a pretty powerful tool. However, we work with water, right? And so the other, really the big physical law that we want to maintain and make sure that we don't violate ever. Here, this is a violation of the idea of viscosity, but we said we can usually get away with that for a lot of flows. But the other one we don't want to forget about was the idea of incompressibility, right? So what we don't know yet is how to build this idea of incompressible flow and conservation of mass into our use of phi. So we're going to try to figure out how to add this constraint to our choice of phi, so that whatever choice of phi we make is satisfies both the conservation of mass and our irrotational assumption. So the way we do this is, as I said, we write for conservation of mass to be true, we must maintain, just as it's written over there, grad dot v equals 0. That is, the divergence of our velocity field has to be 0. Now remember where this came from. This was from saying, all right, I've got, this is from using basically the control volume representations, shrinking it down to a space, splitting it up into two parts, and saying the material derivative of the density is equal to 0. And what falls out is this. So since we're assuming that we're dealing with incompressible flow, this is just how we're going to be writing conservation of mass, for now at least. So if we go ahead and plug in, sorry, I guess the way I should graph this up is by saying that we can get the velocity field from our velocity potential like that, right? So if we go ahead and plug that expression for the velocity field into this conservation of mass, what we end up with is grad dot grad phi equal to 0. And grad dot grad turns into d squared dx squared plus d dy squared plus d squared dz squared of phi equals 0, which we simply write as grad squared phi equals 0. And this is one of the most important equations that you see when you're dealing with inviscid irrotational flow. This is what we call the Laplace equation. And it is the one that we say, all right, we say this is the governing equation for all flows that are both incompressible, or that are incompressible, irrotational, and convective. All right. So, what is this really? This is a differential equation, okay? And more than that, it is a linear partial differential equation. Now, I know you guys said you haven't seen partial differential equations yet, but you remember what one of the properties of linear ordinary differential equations is? If you have something like, x dot equals 0, right? Just a very simple linear ODE. And you say, all right, I have, or let's say you have instead f prime of x is equal to 0. And you say, all right, I have one function of x that satisfies this, and I have another function of x that satisfies this. What can I say about a possible third function of x that satisfies this governing differential equation?
Isn't it like it's a constant plus another constant times that equals 2?
It's some linear. It could be some linear combination of these, right? So what that means is that for any number of functions that satisfy this, we can also say that f3 could be equal to, as you said, like a f1x plus b f2x plus dot 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 any other sum of possible solutions to this problem. So what this means is that when we're looking at this governing equation, if we have phi1, phi2, phi3, so on and so forth, that all individually solve this, then any combination of phi1, phi2, phi3, etc. will also satisfy this. Okay. Now the implications here are huge, because this means that if we're, if we can take individual little solutions to flow fields, and coming with the value of phi, and we can just stack them on top of each other and guarantee that we're still going to satisfy this equation. And I'll show you what that lets us do here in just a second. So I'm just gonna put this back over here before I erase it. This turns into x plus. So this is the Laplace equation written out in vector notation, Cartesian coordinates, and in cylindrical coordinates. Okay, so just for completeness, so you guys have all the expressions that we're going to be seeing it. So it's a little bit hard to appreciate. I can understand that what this idea of having it be a linear governing equation really means for us. But let's motivate this with a quick example. Let's say we have something like, we're interested in looking at let's pick a classic one. The flow around a baseball that has backspin. Right, this is a every, like, I swear I tell us 100 different 5th grade science fair projects, etc. The idea that if we have some baseball that is spinning and we have some incoming flow, so that the flow over the baseball looks like this. Alright, what potential flow allows us to do is there are, and what this linear behavior of our Laplace equation allows us to do, is look at this in 3 different pieces. Okay? Now there are a bunch of sort of special pre-computed velocity potentials, phi functions, that describe special configurations of the flow of interest. For example, we'll look at one phi, and these are the things we're going to cover today. We're going to look at one phi that describes what uniform flow looks like. We'll look at another phi that describes what flow around a apparent circle looks like, and we'll look at another phi that describes circulating flow around a vortex. And what we can say is, all right, I've got uniform inflow, I've got something that kind of serves as a stand-in for a circle, and I've got something that makes the flow spin. And so by combining these 3 things together, what we do is we can reconstruct this flow field. So each of these is going to be, I'll show you today, are very simple functions, very simple phi functions, and it's really easy to compute the streamlines for each of these independently. And so all we have to do then is say that our big phi is equal to phi1 plus phi2 plus phi3. And what we're able to do then is take these sort of cookbook functions, plug them in together, and then we can compute the velocities and streamlines everywhere in the flow field for this case. And by doing that, we can apply then the Bernoulli equation, and we can say, all right, I know that if I know that v is equal to grad phi, I know phi just as a sum of known functions here. I can get the velocity everywhere, I can apply the Bernoulli equation everywhere, I can get pressures everywhere, and then by integrating pressures and such, I can, for example, figure out how much lift is generated on the ball as a result of its backspin. Okay, and this is the fundamental. Let's say this is the big serious tool that fluid dynamicists used, especially in the early 1900s, for calculating things like lift on wings. All right, it was just by taking a bunch of sort of known building blocks, we'll call them, potential flow functions, and get them together in different ways to recreate what looked like very realistic flow fields. Okie doke. So that sets up the problem. Now let's go ahead and get into the nitty-gritty by introducing what these building blocks themselves look like, how we represent them. So we just did all of this. Potential flow is a linear operator. Note here, I do want to point out, so this is the very same stuff we did. Cartesian coordinates over there, cylindrical coordinates. consider this, I don't have another homework ready to go today. So the next homework is going to be assigned on Friday. In the meantime, I'd like you to take a look at example 6.4 in the books. This is one that deals with how to relate the velocity potential and the stream function, and how to use them to calculate velocity at different points and apply the Bernoulli equation to come up with pressures, just given the velocity potential. It's a pretty good illuminating example. Please take a look at it. So a few things to kind of qualify today's discussion. To keep things simple for now, more manageable, we're going to be limiting our discussion to flows that are steady, flows that are in 2 dimensions, and flows that remain in plane, that is in our 2-dimensional plane. Which means that we've only got x and y, u and v to deal with in Cartesian coordinates, or radial and angular velocities in cylindrical. Remember, these are also conditions under which our stream function psi exists. 2-dimensional, steady, planar flows that are inviscid. So we're going to, as a result, we're going to be framing the discussion in terms of both our velocity potential and our stream function, because they exist under the same set of conditions, right? So one more thing about this. We showed, that the what I just showed up on the board was saying, okay, we have the potential flow function, or the velocity potential, which automatically satisfies irrotationality. Let's add a constraint to make sure it satisfies conservation of mass. And what we ended up with was the Laplace operator over there, the Laplace equation. Let's quickly do the same sort of thing with our stream function. So the stream function, remember, psi automatically satisfies conservation of mass. This is guaranteed by the way we define psi, where u is equal to d psi dy, v is equal to negative d psi dx. So if we say, all right, let's add a constraint now to make sure that it satisfies irrotationality, what we do is we say, okay, irrotational flow requires that du dy is equal to dv dx. We substitute in the stream function, we end up with this expression right here as a constraint on our choice of psi. This is also the Laplace's equation, right? It's the same thing we have written over there for phi. So what this means is that under the assumptions of plane irrotational flow, that is, satisfies conservation of mass and is incompressible, both the stream function and the potential flow function, phi, satisfy Laplace's equation. So we can use either one. So for that reason, we're going to be carrying along both phi and psi in the functions that we introduced today. Okay, we talked about this on Monday. All right, and as I said, the reason that we care about the Laplace equation and its linearity is that it allows us to build solutions out of smaller known solutions. And in doing so, to sort of build up these bigger, more complicated solutions. We just did all this. There we go. Okay. So what we're going to try to get through today are the introduction of the 4 big building blocks that we use to construct these solutions from smaller known ones. Uniform flow, sources and sinks, vortices, and doublets. With these 4 sort of canonical forms of the flow field, each of these has a pre-computed function of phi and of psi, right? So we can just go to a table by the end of this, go to a table and look up a value of phi, a value of psi for each of these, modify it by a couple of parametric tweaks, and then plug it into our flow field to represent, for example, the flow around a circle. So one way that to kind of motivate this, another one, besides the idea of the flow around a baseball, one way I use this in my research is, I think I've shown a video of this before, right? This is an experiment that I've been working on in different iterations in the towing tank for the last couple of years, where this is a sort of a rudder-like geometry that sticks down into the water. It's a surface-piercing hydrofoil, and under certain conditions it gets this big aerated bubble grown around it, right? Where this is a cavity filled with air. And by leveraging some of the ideas of potential flow, what I was able to do is say, all right, I can build up a solution, an approximation of this flow out of several hundred smaller little piecewise approximations using vortices. And in doing so, I'm able to recreate a flow field that mimics this one, with this one to within a few percent. Okay, so using a theory that's turned 100, years old, just I think last year or something, we're able to still get really powerful solutions out of it. So, okay. So enough prefacing. Let's jump into this. So, 4 things we're going to talk about. I'm going to write them up here and check them off as we go, so we have something to measure against. Uniform flow, source, sink, vortex, and doublet. Okay, uniform flow. This is the easiest and of the potential flow functions that we're going to be dealing with. This is the case where, as the name implies, we have some velocity that is not changing in space, right? It's either all going this direction or all going that direction. It doesn't matter. So we have something that is defined by a constant u and a constant v. Right? Where these do not change in time or space. And so let's, just for this really general case, if we know that u is equal to dphi du, dphi dx, then what this leads us to conclude is that phi is equal to ux plus some function of y plus a constant, right? Using the same sort of integration of different pieces of this that we did on Monday. If we know that v is equal to dphi dy, then integrating allows us to say that this is equal to some function of x plus vy plus c. And so combining these two estimates of phi, we can determine that phi is going to be equal to ux plus vy plus c. So for the special case shown here, let's say that u is entirely in the x direction. That is, that the vertical velocity v is equal to 0. Okay, this means that the flow magnitude we say this here is simply equal to the magnitude of the flow. This is equal to 0. Carrying this through, what we see is that we end up with this function here, where phi is just equal to big U times x plus c. Remember, the velocities here are calculated as the gradient of this, in which case the constant disappears. So the constant we choose is almost completely meaningless. It's not going to do anything for us. So the easiest thing to do is when you end up with a constant in your potential flow, just set it equal to 0. Okay, so let's go ahead and just kill this. And what we end up with then is that phi is equal to ux plus vy. So for the case where u is entirely in the x direction, it turns into ux. Looking at this from the perspective of the stream function, is it alright if I erase this, guys? It's all up there. Conversely, remember the stream function tells us that u is equal to d psi dy, and v is equal to negative d psi dx. So, again, following the same procedure with u, v, just integrating with respect to y and x, what we end up with is psi is equal to negative vx plus uy, and we'll leave the constant out and just assume that's equal to 0. So if you look at those two things, or you know, in this special case where u is entirely in the x direction, it's just becomes a function of y. All right. So if you look at these two functions that describe the same flow, right? If you plug in our way of getting the velocity, these are just describing exactly the same configuration of the flow. Uniform flow in the x direction with a magnitude u. The only thing that we change is we've changed the convention we use to get the velocity out of the function itself. But if you look at the functions, remember the lines of constant psi give you streamlines, right? Constant psi here means at each value of y, you plug in a constant y, you're going to get a constant psi equal to u. So those describe different horizontal lines like this, which on inspection we can say, yeah, those look like streamlines. We said the flow is only in the x direction. We get horizontal bars for streamlines. I can deal with that. Remember that lines of constant phi we call equipotential lines. And equipotential lines are always orthogonal to streamlines. This is one of the takeaways from the last lecture. So if we plot out lines of constant phi, what we get are these vertical bars, right? Yep, those look orthogonal to the streamlines, so we can say that that assumption still holds. All right, if we plugged in a more arbitrary u and v here, something that wasn't just in the x direction, we would get the same result. We would say that, you know, because we said v is equal to ux plus vy, you can see that here, negative vx plus ux plus vy, if we figured out the slopes of constant phi, constant psi, what we would get is the slope of one would be the negative of one over the slope of the other, which means that they are always going to be orthogonal. All right, so just to kind of drive this point home, let's say we turn the flow at some angle relative to the horizontal axis. Okay, that is now u is big U cosine alpha, v is big U sine of alpha, right? This makes sense? So just plugging in different values here now, we would get cosine alpha, big U sine, oops, not theta, alpha, plugging in the respective values for equal to by x. All right. So integrating with respect to either x or y, what we get for both for a function phi is now just u x cosine alpha, y sine alpha. And for phi, this leads to the expression here where, once again, we just have the y leading here and the negative x leading here. So if we drew again lines of constant phi, what we would get is the blue bars here that are oriented at some angle alpha from the x-axis. And so looking at that and saying, all right, these lines of constant phi come from prescribing the velocity pointing in that direction. We again say, all right, yeah, these make sense as streamlines. And if we plotted out lines of constant phi, we would get these black dashed bars, which are orthogonal to them. So again, the observation holds. This is pretty easy, pretty boring, but it's amazing how uniform flow still manages to kind of get lost in the shuffle. So before we move on, yeah.
I had a question on the slide before.
Huh?
I had a question about the previous slide.
Yeah.
So those equations in the red box.
Yeah.
That's, only for flow in the x direction.
That's for flow just in the x direction.
So if it were in the y direction, like let's say uniform flow straight up, there'd be
UY.
and be ux.
And this would be negative ux because the v is defined as negative psi dy. Right. And you can actually get the same thing out of here, right? If you plug in 0 degrees for alpha, then what you'll get is this will disappear, this will go to 1, you'll just end up with ux. If you plug in 90 degrees, this will go to 1, this will go to 0, you end up with uy. Same thing here, 0 degrees, this will go to 1, this will go to x, you get uy. 90 degrees, this will go away, you have a negative 1 here. So. Their uniform flow. The next one we're going to talk about are what we call sources and sinks. This cool little video shows the way what we mean when we talk about a source or a sink. This example of a source shows like a little orifice in a plane of fluid that is blowing water out of it, right? So there's water coming out of a point, and it's being put in a uniform flow. And what we get is this sort of pushing of the streamlines away. And so, for example, the fact that now the streamlines go around this, this sort of what we call a Rankine half oval is an example of the way that real flows kind of follow this idea of putting different potential flows together. This is uniform flow. If you plug a source into the middle of it, you get some new flow configuration. So what a source represents, just like in this case, is the idea that if, let's imagine we have a line that is running into the board, right, infinitely, and we're taking a plane cut through that. Now imagine that there's mass flowing out from this line in all directions. Okay, so just like the sketch shows here, what we get are these velocities that are emanating radially from a point in space. So if we've got, let's say we've got some circle, it's got a radius r, and at this circle it has a velocity vr. What then is the volumetric flow rate through the circumference of the circle? It's just going to be, think of it like a controlled surface, right? It's going to be the velocity normal to the surface times the area of the surface, right? In this case, instead of area, we've got length, because this is mass per unit length. But the circumferential length of the circle is just 2 pi r or 2 pi big R. And the velocity flowing normal to that is vr, right? So this is kind of, it's a weird change in convention. I'm sorry, but this is what the book does, and I'd rather stick with its convention. We now define this sort of volumetric flow rate per unit length, right? This is, because we're dealing with a two-dimensional plane, there's no such thing as a volume. So the closest thing we have is, we say volume per unit length. Our volumetric flow rate per unit length we call little m for this case. And so if we have this length, or this amount of mass flowing across the boundaries of any circle we draw, then by changing, if we change the size of our circle, conservation of mass says that m cannot change. So what has to change here is, since we'll say that this is R1, this is R2, what we now have to get is that 2 pi R2 times VR2 is equal to the same thing, right? The amount of mass flowing across the boundaries can't change, because whatever has to go through here also has to go through here, also has to go through a bigger circle here. And so what we end up with is that for a given mass flow rate m, or a given volumetric flow rate m, V sub r is equal to m over 2 pi r. Okay? So this is the velocity flowing, the radial component of the velocity Vr. And the way we've set up this problem, we've said that V theta is equal to 0. Note, if you haven't picked up by now, we're dealing in cylindrical coordinates for this problem. So if we say, all right, let's plug in our known, our expressions for the radial and angular velocity as functions of phi, our velocity potential, we say that V sub r is equal to, in this case, V sub r is equal to d phi dr, v theta is equal to 1 over r d phi d theta. So Vr is equal to d phi r, and d theta is equal to 1 over r d phi theta. Is equal to m over 2 pi r is equal to 0. So, same process of integration with respect to r for this case, respect to theta here. What we end up with is phi. By integrating this, we're going to get phi is equal to integral of m over 2 pi 1 over r dr. Integral of 1 over r gives us Yep. M over 2 pi ln of r. Integration of this with respect to r, or with respect to theta, is going to give us, nothing. So our velocity potential ends up being expressed here, which is exactly what I've written right there. And so this is, again, and this is just another one of our sort of cookbook formulas for phi that we can select, and we can add to, for example, our expression for uniform flow. So if we wanted to write out the equation, the velocity potential to describe this flow, we already have all the tools we need. We just plug in our uniform flow, right? We could say if phi is equal to phi of uniform flow plus phi of a source, where uniform flow would be in this case like something like negative ux, and our source would be written like this, then by coming up with, we'd have to cast them all either into Cartesian or cylindrical coordinates first. But that's not that hard, that's just bookkeeping. We would actually come up with a flow field that looks just like this. So we describe this velocity potential function by saying, all right, there's really only one sort of parameter we can change, and that's m. So m we describe as the strength of a source. If m is positive, that means that flow is coming out of it, it's behaving as a source. If m is negative, that means that flow is disappearing into this point, and all the radial flow is going in towards that point. And that's the case we call a sink. All right. So if this is the parameter we get to play with when we're plugging this into a function. We get to say, we get to choose where it goes, right, where we put this source, and that kind of constrains how we compute r, and then we get to play with how large of a perturbation to the flow it actually is by playing with our value of m. And so those are details that we're going to get into in the next lecture. But for now, let's write that down. That's our description of a source or a sink. We should mention, if we go through the same process with the stream function, we the r we said is in this case the stream function is computed as 1 over r d psi d theta. The angular velocity is negative d psi dr. So going through the same integration, comparing the integrals, we end up with is finding that psi is equal to m over 2 pi theta. All right. What happens if we draw out the streamlines and the equipotential lines for this velocity potential? Well, based on the setup of the problem, what do you think the streamlines are going to look like? If we've got a source placed right here, how would I draw the streamlines? Just what in general do you think they're going to look like? Right, radial lines emanating out from the point of the source. And our equipotential lines, we can sort of get from saying, all right, we've already established that the equipotential lines are, so these are our streamlines, which are constant psi, right? We get those from plugging in. If we make one of these constant, that just means we have to fix a constant angle here, so those end up being these radial lines. We've already established that lines of constant phi are orthogonal to lines of constant psi, so that the only thing that can be orthogonal to these everywhere are concentric circles, right? So these are lines of constant phi. There's one thing I want to sort of point out here, and it's I know somebody would be probably be bringing this up by the end of class if I don't kind of head it off at the pass first. Does this whole construct seem a little bit funny to anybody in terms of conservation of mass? We've just said here that this whole thing has been derived under the idea that mass is conserved, right? But we've got mass either coming out of or going into a little point in space, which seems like a violation of the whole idea, right? That's because these functions, and almost all of these functions, this one, are all built around what we call mathematical singularities. These are, that is, for example, let's look at the velocity potential here. anytime that the value of r goes to 0, these potential flow functions that we're introducing are pretty much going to blow up. They become usually infinite. If you look at our radial velocity here, if r goes to 0, this becomes infinite. Yeah? Which isn't physically possible. So there's sort of this paradox going on. We say, well, we set up a governing equation that's built around irrotational flow with conservation of mass, and then we propose all these solutions to the equations that violate those very assumptions we've made. And this is true, and there's not really a good way of, there's not a perfect way of getting around it, but by some kind of clever mathematical trickery later, we're going to show that the way we can get around this is by just avoiding, we never actually look directly at the point where r is equal to 0. Okay? They're singular at r equals 0, they're infinite, our governing equation is violated, but anywhere that r is not equal to 0, it doesn't matter how far away from r it is, it could be almost exactly 0. Anything that is not actually at the point of the singularity satisfies our governing equations. So what we'll do is, because that point has 0 actual, it takes up 0 room, right? It's an infinitesimally small point space, our singularity. We simply, when we're doing integrations and such, we simply figure out a clever way of removing that point itself from the integration domain, so we never actually have to mathematically treat this. We always sort of leave r equals 0 out of our solutions. An example could be like if the in the case of the baseball, right? This baseball with backspin. If we figured out a way of using a source and a sink to represent the baseball itself, so that we had, or I said we'd have something that, if this is the baseball, we're going to end up with, this is an example of what's called a doublet, and we have our uniform flow coming in. All our singularities are contained inside of the representation of the baseball. That is, they're out of the actual fluid domain. Okay, so what we usually, the easiest way of doing, getting rid of this inconsistency of a singularity is by saying, let's let it be inside of something that we're not concerned with, like a solid, right? Our representation of a solid. Let's remove it from the fluid domain either that way or by some other special math tricks. We don't need to worry about those math tricks just yet. We'll get into them in due course, but just recognize that all of these methods, they're going to violate our assumptions only at a single tiny little point in space. All right. So that gets us through the source and sink. So let's very quickly here look at an example where we might use a sink to simulate a realistic flow. So let's say we've got this wedge in space, right? It could be something like it could be like a drain, right? At the corner of a body. Let's say that our sink is located right here. So what we've got is this flow that is described by a velocity potential, -2 natural log of r. So what we're asked to do here is determine the volume rate of flow per unit depth or unit length into the board here that goes into this opening using the potential function. And for the sake of time, we're going to leave out part B, but let's just get through the potential flow part of it first. So the way to look at this is sort of as a control surface problem, right? We only have one control surface we're really worried about, and that is this A and B. So the way that we figure out the volumetric flow rate from out here to this point here is by computing the flow across AB. So if we take the integral from A to B of V dot N d, I guess it's an area, which ends up being, say, length times the length into the board. What we get is an integral. We turn this from an integral from 0 to whatever our we'll say that this angle here is beta, which is equal to pi over 6 in this case. Beta VR negative VR times R d theta. Which in this case is just going to turn into, we have V sub R is equal to the derivative with respect to R of this, which gives us to 0 to pi over 6 negative 2 theta is equal to simply negative 2 times pi over 6, which turns into negative pi over 3, right? With units of, in this case, length squared, or dimensions of length squared per time. So all that we did there, sorry I'm kind of going through this quickly, but we're got to get through vortex and doublets still. The idea here is that we know the radial velocity as a function of r. So the function itself becomes independent of the distance r of our control surface from the source. And that comes from the same idea of conservation of mass. It doesn't matter whether this control surface is here, or whether it's in here, or whether it's in here, the same amount of mass has to flow across it. And so that's why our result here becomes independent of the radial distance from the sink. This example is also in the book if that quick little run through leaves you a bit confused. All right, the next potential flow function of interest is the vortex. And this is my personal favorite. If you can have a favorite potential flow function, everyone should. So the way we get to vortex flow is, remember we said, all right, for the source and the sink, we ended up with streamlines and equipotential lines that looked kind of like this. Right? Our streamlines were these lines pointing out from the origin, and our equipotential lines were circles. What happens if we simply switch the functions? Right? We'll get streamlines that look like circles, equipotential lines that point out radially from the origin. And so, if we go ahead and do that, that is, here, let me sort of write it out schematically up here. We had phi for a source is equal to m over 2 pi ln of r. Psi of the source is equal to m over 2 pi theta. We want, let me move this. Okay, so what we want now is phi of a vortex and psi of a vortex. So in the source case, we ended up with equipotential lines that were circles around the origin, concentric circles. So we want to make those look like our streamlines, right? Circles. We ended up with our streamlines for the source looked like lines emanating from the origin. And so we want those to turn into our equipotential lines. Radial lines. So what we end up with is defining phi the vortex equal to, we're not going to use m. What we use is just a change in convention where we say this is now equal to k theta, and psi vortex is equal to negative k ln of r. Now this might seem a little bit arbitrary, but we get to the same, we get to the exact same values for psi, or for phi and for psi, if we work, from the ground up. If we say that we want a purely angular velocity, no radial velocity, and then integrate to get our potential and stream functions. I'm just trying to save us a little bit of time here by saying we already know what the flow field looks like, and we know what we want it to look like. We know what functions give us those behaviors. So K is what we call the strength of our vortex. Just like M was the strength of our source of sink, K is the strength of the vortex, and the sign of K determines whether or not it's counterclockwise rotating or clockwise rotating. And just as the name implies, you've probably all seen vortices anytime you've pulling the stopper out of a drain. But the idea of a vortex is that it creates this fluid rotation without any flow radially occurring from the vortex itself. So the thing that's kind of interesting here and may not be very intuitive is note that what we get for our, radial velocity is always 0 by definition, and our angular velocity varies with 1 over r. That means the velocity out at the edge here is actually smaller than the velocity in towards the center. And this is a special case of what we call a free vortex. The free vortex says that the velocity close to the center is larger than the velocity further away from the center. If you think about hurricanes, for example, right? Where are the wind speeds of a hurricane strongest? Wall of the eye, right? It's because hurricanes, at least a large part of them, act like free vortices. The amount of, it's sort of a kind of a way of thinking about that. The angular momentum is, if it remains approximately constant, that means it has to be rotating a lot faster towards the center than at the outside. And this allows us, this idea of a free vortex also allows us to clear up a really confusing idea, and that's like how the hell is a vortex irrotational? We said, this whole idea is built on the idea of irrotationality, and here we are talking about rotating vortices. So this, whether or not you were thinking it, is an excellent question. Oops, we don't need that. And so this brings us to what makes a free vortex special. Okay, there are two kinds of vortices in nature. One is the free vortex, the one we just derived, and the other is what we call the forced vortex. A forced vortex would be what happened if you took a bucket, and you filled it with water, and you spun the whole bucket. It's basically rigid body rotation of the liquid. Okay. So one of them, the velocity at the edge is greatest. One of them, the velocity towards the center is greatest. Okay, so this is where this sort of, we make this distinction. Remember, irrotational flow was derived around the idea that if we drew a tiny little element of fluid, right, stuck in a velocity field, that as this element flowed through the velocity, its orientation wouldn't change. So irrotationality has nothing to do with the path this element takes. It has to do with orientation of the element as it takes that path. So this distinction is really important. flow orientation, not the path, just determines whether a flow is irrotational. And because of the way the velocity towards the center is greater, if we created a free vortex here in class, if I took a bucket and I poked a hole in the bottom of it, and we ended up with, you know, a whirlpool-like motion, right? It's a good example of a free vortex. And I stuck some floating thing into that vortex. What we would see is that it rotates around without changing its, it doesn't rotate. It moves around the edge of the vortex without changing its orientation. And this up here is a really good example, if I can get it to play. There we go. Okay. So this little animation here shows the difference between a forced and a free vortex. This is an example of a forced vortex. For example, as I said, it's like the rigid body rotation of a fluid. If I took a bucket and I spun the entire bucket so that the velocity at the edge matched the bucket speed, our flow field would look like this. And if I stuck something into the bucket to rotate with the flow, unsurprisingly, some little floating ABC or AB marker, then it would rotate with the flow. However, if I made this a free vortex, the kind that we describe with a potential flow function, because the velocity is greater at the center than at the edge, the part of our little element that's closer to the center is always getting pushed along a little bit faster with its radial velocity, okay? And because the velocity is greater here by a distance that is, or by an amount that's proportional to the distance, then what this means is that the orientation of the element never actually changes. So this is an example of how we can get away with calling a vortex flow irrotational, because any element of the flow never actually changes its orientation. It goes around a circular path. Yes, circular paths are okay. Circular paths, while it does this, are not irrotational. Yes, irrotational. All right. Okay, so we have free vortices and we have forced vortices. Free vortices are irrotational and therefore have a velocity potential function. A forced vortex we cannot describe with a velocity potential because it is rotational flow. Right? We also have these sort of hybrid vortices in nature, and this a more correct way to talk about something like a hurricane is by using what we call a combined vortex, where it behaves like a free vortex, sort of in a vast majority of the field, but down here, right towards the middle, in the actual eye, it behaves like a forced vortex here. So as a result, I think Google actually allows you to, I think it was with Matthew, you were able to look at like these cool data dumps of wind speed measurements and stuff, and they had the hurricane went right across, like the eye went right across one of their wind speed measuring stations, and so what you got was something like if we say, let's say this is our this is a hurricane, and we were to take a cut across it, and we were to plot the velocity across this cut, the angular velocity, as a function of this x. What we would get is we would get something that looks like this. I should make this symmetric. All right. where this region here would be the width of the eye. Okay, so yes, the velocity is greatest at the wall of the eye of a hurricane, where it goes from acting like a forced vortex, where the velocity is sort of proportional to the distance from the exact center, to where it starts acting like a free vortex. This is also a special, there's a special mathematical model that describes this. It's called, there are different versions. There's what's called a Rankine vortex, and others are called like Berger's vortices. You'll probably see some of those in 321 later, but just so you've heard the names before. So, free vortex, you have this decrease in radial or angular velocity as you get away from the origin. Forced vortex, it increases. Combined vortex, you have some region where it behaves like a kind of a rigid body rotation, and then outside of that limited region, it behaves like an inviscid irrotational vortex. Okay. So, oops. There's also this idea of what we call circulation. Okay, and circulation we define as kind of it's an integral term that describes how much rotation is actually present in a fluid. So circulation we define by this sign big gamma, capital gamma, which is equal to the integral along some closed contour. This symbol here means a line integral around a closed contour taken in a counterclockwise direction of v dot ds. Which means if we've got some curve here, then that means we take an integral along the edge of the dot product of v with the tangent vector along that curve. And what we should get is that for any irrotational flow, the circulation is going to be equal to 0. Okay, this goes along with the idea of irrotationality. This is the case for any closed contour that does not include a singularity. However, as I said before, a vortex, just like a source or sink, is actually a singularity in that we can't really, at the very center of the flow, it violates the idea of irrotationality and our governing equations. So what we get is, if we picked first to do an integral around this path right here, what we would see is that if we said that if we took this integral around the path A, B, C, D, we don't really have time to do it rigorously, but we know that from A to B, C to D, our velocity along those paths is equal to 0, right? Because for this vortex, all the flows are on circular paths, so we don't have to worry about this and this. We know that the arc length of dA is smaller than the arc length of BC, but the velocity here is greater. And the velocity, because we say the theta varies with 1 over r, and that the actual arc length, we'll say, the arc length varies with r, the product of the two, that is v times the arc length, is going to be equal for the two of them. And so the current term from dA and BC will cancel one another out, and what we'll get is that this equals 0 going around this path. Now this makes sense because we showed earlier, this is an irrotational flow. So this is just a way of kind of verifying that for the irrotational flow, our circulation is equal to 0. However, if we took an integral around this path, right, what we would see is that in this case, our velocity is simply equal to be theta, which is going to be equal to, what was it, k over, yeah, we said k over r, and so this is constant, the velocity is constant here, and then the arc length is going to be equal to s is equal to 2 pi r, right? So the product of these things is going to give us that the circulation is equal to 2 pi k. Same thing shown here. So this gives us, this is sort of a way of relating the circulation of a path that contains this singularity to the strength of the singularity itself. We can say that we can therefore use either the circulation of a vortex or the k vortex strength, either one, to define our potential flow and stream functions. This is kind of a an issue of semantics, but this is a kind of a powerful notion. The idea that if we take any integral, right, one closed path, for example, could be one that looks like this, right? This sort of Pac-Man when he's not hungry. And the closed integral around here, because it doesn't actually, we cut out the singularity here. The integral of the circulation here is going to be 0. However, if we join these two, now we get a non-zero circulation. So it's kind of a way of either accounting for or ignoring the effect of the singularity itself, depending on what we want to do with it. To go back to the example of the baseball with backspin, what we would usually do is we would keep the singularity in our integral, and we would say, all right, this baseball has some circulation that is equal to some function of the vortex strength that we put at the center of it. And then there's a classic theory called the Kuta-Joukowski law, which tells us that the lift on a baseball or on anything that has rotation is proportional to the circulation around it. And so that's how you get the idea that the backspin on a baseball creates lift, is by saying, I can model it with a vortex in the middle of some other body that creates circulation. Circulation leads to lift, and it all kind of makes sense. All right. So that gets us at least kind of through vortices and circulation. And the last of our 4 building blocks now is the doublet. So the doublet isn't really a unique singularity or a unique potential flow function on its own. It's more a clever way of combining two that we've already talked about. So the idea is if you take a source and a sink, source, emanating flow, sink, swallowing it up, and you put them really close to one another, and they have equal strength, right? Remember, the strength of a source or sink is determined by n. I should mention, the doublets here are easier, the derivation here is easier to work out working with the stream function. But I'll give you the potential flow function that describes them on the next slide. But for the derivation here, let's consider the stream function of a source or a sink. Remember, the stream function of source or sink is equal to either a positive or negative m pi theta. So if we put two sources, if we put a source and a sink of equal strength, equal values of m, at two locations close to one another, then what we get, and let's say we are evaluating a stream function at some point p here. So what we get are two different values of theta, which show up in here. So by linearly combining the stream functions for the source and the sink, we get this function. What we can then do is simply take the tangent of both, rearrange and take the tangent of both sides. So moving this over here, right? Psi 2 pi over m now, and we have just the thetas over here, taking the tangent of both sides. We can apply this trigonometric identity to expand this tangent, the tangent of the difference of two angles, into this expression here. Then we just sit here and we do some geometry. We say, well, let's look at the kind of the size of these. We look at the size of these respective triangles. We say that from this point, you know, that this here is equal to r sine theta. This is equal to r cosine theta minus a, where a is the distance of the sink from the origin, and that this triangle is r cosine theta plus a, this leg. So by just kind of looking at it and inspecting the different lengths and using trig, there shouldn't be anything too complicated here. But we can say that tangent theta 1 is equal to this height divided by this distance, which turns into this, and tangent theta 2 is this height over this longer leg distance, equal to this. Plugging these all in, we end up with this expression here, where the tangent of 2 pi, negative 2 pi psi over m is this expression that's a function of our radial distance, the distance that the sink and the source are away from the origin, and our angle. We can take the arctangent of both sides so that we isolate our stream function once again, this expression, and then finally we can make the assumption, right? The assumption is that a, the distance, if these, the source and the sink are located at a distance of 2a away from each other, we want them to approach almost the same point in space, because we want to treat this as sort of one potential flow function. So if we let a become really, 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 really tiny, then the quantity inside of here becomes really, really tiny, and the small angle approximation applies. So we can just say that the inverse tangent of whatever's in here is about the same as whatever's in here. Which allows us to write this. Which gives us this expression up here. And then finally, if we say now a, we take the limit as a approaches 0. Okay? We want the limit as the source and the sink approach the exact same point in space. Then we get the limit of, as our a approaches 0 of this, gives us the stream function for a doublet. A similar process gives us the potential flow function for a doublet. And what's cool about a doublet is that because we have a source over here and a sink over here, streamlines now, you know, velocity comes out of one side and it goes around and it goes back into the source, or into the sink. And what it may not look like it here, but if you put this into a potential flow, into a potential flow with a uniform flow, what you end up with is, if your uniform inflow looks like this, and you have a doublet here with a source and a sink, then what you're actually going to get is, because of the way these streamlines behave, is this is going to turn into a perfect circle. And so this is the way that you represent a circle or a cylinder in a potential flow, is by plugging a doublet in. Okay. So to kind of summarize all this, we have the four building blocks of our potential flow. We have uniform flow, source or a sink, and vortex, and a doublet. And so from the example that I showed at the beginning of class, where you have like a back-spinning baseball flying through space, we can see that is the sum of the uniform flow to represent the incoming flow. It's a doublet to represent the baseball itself, and it's a vortex located at the center of the doublet to create the idea of backspin. And so just by summing this